fourth day of the second annual iHeart Pluto Festival. My name is Kevin Schindler, and I'm the historian at Lowell Observatory and pleased to host this event. Tonight, I'm speaking from the Lawrence Lowell Telescope Dome, better known as the Pluto Discovery Telescope Dome, because this telescope right behind me, or astrograph or camera, or whatever you want to call it, a type of telescope used for taking pictures. Anyway, this is the instrument that Clyde used to discover Pluto on February 18th, 1930. So we're really pleased to celebrate Pluto this year with our second annual event. We're really celebrating both the science and the cultural heritage of Pluto, because Pluto has really entered so much of our lives, as it were. This event, it goes on every night through the 18th. We've got anywhere from one to several different presentations each night. We also have ongoing events throughout the week. One of these is with our friends down at Karma Sushi Bar Grill in downtown Flagstaff. If you're in the neighborhood, drop by there this week and you can get a Pluto roll, because Karma Sushi is the place where Clyde Tombaugh ate the night he discovered Pluto, although it wasn't a sushi place then. But Karma Sushi honors that heritage with the Pluto roll. We've also got the International Association of Astronomical Artists, who have an art exhibit. It's displayed in the Lowell Observatory gift shop area, but we also have it virtual, since we don't have visitation going on right now. Just go to the iHeart Pluto website. You can see that art exhibit there. And then the third event that's ongoing is our local amateur radio group is broadcasting actually from our parking lot right now. All this week they're broadcasting to amateur radio folks around the world, so you can tune into that. Besides this, we also have our gift shop with all sorts of specialty items with Pluto t-shirts and books and other stuff. One of the things that we have in there, I'll point out, is this book, Pluto in Lowell Observatory. And one of the authors of this is our speaker tonight, Dr. Will Grundy. Will has worked at Lowell since the 1990s. He's a planetary scientist here, specializing in the physical properties of icy bodies in the outer solar system. He's involved in a lot of different projects and research that uses telescopes, uses laboratory equipment, and also telescopes, as it were, in observing things in space. Especially the New Horizons mission. Will is the surface composition team leader for that. So he's at the center of Pluto and all the research going on. So we're really excited to have Will here tonight. We're going to, learn all the latest about Pluto. If you have questions throughout this, just type them into the chat box in YouTube, and we'll ask some throughout the program as we can, and then also some at the end. So with that, let me turn it over to Dr. Will Grundy.
Okay, hang on a second. Let me share the screen. So hopefully you see that now. Right, so Kevin asked me to talk about Pluto after New Horizons. And that's the era that we're in now, I guess. Let me back up just a little bit and just say the bare minimum about the New Horizons mission. I won't talk about the long and arduous course to get to the launch pad, but we launched the spacecraft back in January of 2006 and had a flyby of Jupiter a little over a year later. And then cruising across the solar system, which is a big place, about 8.5 years of, are we there yet? And then finally, the Pluto encounter in summer of 2015. And you notice Pluto's orbit is tilted a lot with respect to the plane of the solar system. We encountered Pluto basically right as it was crossing the plane of the solar system, which was really convenient because that meant that the spacecraft trajectory didn't have to get tilted out of the plane of the solar system, which would have cost more propellant. And it also meant that the spacecraft would continue through the plane of the Kuiper Belt, the disk of small bodies that are out beyond Pluto for the most part. And we had an encounter with one of them called Arrokoth in right at New Year's of 2018, 2019. I won't talk about that at all, but this is the context of New Horizons, and we learned a tremendous amount about the Pluto system. And I'm going to distill them down to just 2 slides, really, because I want to go to the beyond New Horizons era. But Pluto turns out to be an amazingly complicated little planet with all kinds of processes going on. And there were a lot of people that didn't really think that that would be possible because it's just so far from the sun. It's so cold. What would be the energy that would drive that? But it turns out that the ingredients on Pluto's surface and in its atmosphere are so mobile that it doesn't take a whole lot of energy to move them around and create a lot of active geology, and also complex structures in the atmosphere and all kinds of seasonal cycles and so on. So really a very interesting place to study. For a planetary scientist, what could be more fun than exploring a new planet with all kinds of mysterious new processes that you need to figure out? The rest of the system had all kinds of excitement too. I mean, Charon would have been a very interesting planet even in its own right, even if Pluto wasn't there, with all kinds of interesting geology happening in different eras. The dark reddish pole that's the result of gas that escapes from Pluto and gets captured temporarily by Charon's gravity and gets processed while it's there. A whole slew of small, bright, icy satellites that are just spinning wildly with different spin poles and spin rates and not at all regular. And this sort of messy aftermath of a giant collision that's really essentially what we think also formed the Earth-Moon system, although we didn't get lucky enough to get a whole bunch of little small satellites too, or if we did, they've long since been lost. So a lot of what we learned with New Horizons is captured in a new book, a major new textbook in the space science series from the University of Arizona Press. Now, when I was starting grad school, any serious planetary science professor had bookshelves full of these space science series books on all the different bodies that had been explored by spacecraft and even ones that hadn't. So it's a real thrill to put another book on that shelf finally, and essentially retire this one, which was the Pluto volume that you would hand to any starting grad student up until now, which came out in 1997. So what I want to talk about now, though, is that it's not like when we wrote the textbook, we're done. Pluto research is going on and all kinds of new proposals are being proposed, new discoveries are being made. People are figuring out how some things work that we saw and had some ideas about that were maybe wrong or maybe right. And then I'll also talk a little bit about what the more distant future holds in terms of new telescopes and potential future missions and so on. Okay, so there's a bunch of different topics. So please feel free to ask questions while I'm still on the topic, because I'm going to sort of jump around to different topics every few slides. All right, so one of the things that we saw early on was these bright mountains on Pluto with bright peaks. And we had the ability using infrared spectrometry to see what things were made out of. And this is a map of methane ice, and you can see that it corresponds to those bright peaks. So it's bright methane ice capping these mountains. And of course, here's a picture of the Alps in Europe with water ice snow on top of the peaks, and the similarity is pretty striking. But it turns out that the mechanism is quite different. So let's review how these things, and this is in a paper by a guy named Tanguy Bertrand last fall. So on Earth, it's warmer closer to the ground and it's colder as you go up. And the reason for that is that if you take a parcel of air and you lift it up, it expands and cools. And that's a very normal process. That's also how refrigerators work. But there's more water vapor in the atmosphere generally when it's warmer, and you just can't have as much water vapor in the atmosphere when it cools. So if air is trying to blow up over a mountain, it goes up, cools, and loses its payload of water as snow or rain or frost forming on the peaks. So, of course, that's what we thought was probably going on Pluto. But Tanguy Bertrand took global circulation models, which are the same models that are used for weather forecasting and climate forecasting on Earth, and applied them to Pluto. And it turns out that the atmosphere gets warm fairly quickly at not super high altitude, and you can have a lot more methane in that warmer air, and the mountains are tall enough to poke up into that warm methane-rich air. And especially at night when the mountaintops are radiating their heat into space and they get cold, some of the methane freezes out onto the mountains, and also that cold air flows down the slopes. It's called a katabatic wind. Can be kind of a strong wind even. And so it's really a very different process from what you see on Earth. Another thing that's looking very similar to Earth, and we commented on it early on, but we weren't sure really how it works, is this apparent, looks really to the eye like sand dunes. And it's most notable in the northwest edge of Sputnik Planitia, that big flat glacier that's really the heart of the encounter hemisphere of Pluto. And this guy, Matt Telfer, did a paper recently where he worked out that these probably are dunes and what they're made out of and why they're there. So the reason that they're there is that the mountains are here, and you get these same katabatic winds blowing down from the mountains and out across this plain. And you see that the dunes are more or less perpendicular to the wind direction. Those are called transverse dunes. That's fairly normal kind of phenomenon that you see on Earth as well.
Well, we've got a question before you get too far away from the mountains.
Yeah, go for it.
Kind of a fun question from the Pluto diaries. What would it be like to climb a mountain or ski down the slopes?
Well, the gravity's a lot less, so you could probably fall and not hurt yourself quite so badly. Some of these mountains are pretty spectacularly rugged, many kilometers high. So I'd imagine that the scenery would be really something. And if you're going downhill, the wind would be at your back, so that might be kind of exciting, speeding you up more than you wanted to go. I like to ski kind of slow so I can look at the scenery. All right, so again, mapping where the methane is, it turns out that this pink is where methane is, and the areas that were mapped with the dunes are more or less the pinkish areas here, and you can see further out into the middle of Sputnik, you don't get quite so much methane. And you also see these concentrations of methane in the mountains and some of the steep slopes that might be the source of the grains. Methane's ice is unusual because it's very low density. It's maybe, I don't know, like a sixth of the density of sand grains. And in Telfer's paper, he did the calculation of what kind of wind it would take to make those things move around. It turns out that it takes a lot more wind to initiate motion than it does to keep motion moving once it's going. And so this bottom curve is how much wind speed is needed for a given particle size of a methane grain. And you can see that the dashed line is how fast we think those katabatic winds blow. And so really big grains and really little grains won't move, but grains in this intermediate size, this is about sand size, can move once they've been started. They'll continue bouncing, and that's how you form dunes. Now, the wind never gets fast enough to actually start them moving from scratch, so that's a bit of a puzzle, but maybe there's some landslides or something happening in the mountains that delivers material. And the other thing that they worked out is that the spacing of the dunes is exactly what you would expect for the known gravity and wind speed and particle size in this range. So it all kind of holds together. It really looks like these are methane sand dunes. Moving on to another topic, we early on were pointing to this Bright Mons, which I don't actually have a picture of in here, as a probable cryovolcano. But Dale Cruikshank and Christina Dall'Ore did a series of papers where they pointed out other things that look like possible eruptive deposits. You see here this crater that's apparently been filled in with a fair bit of material, and some of the other craters have sort of flat floors as if they've been filled in. And they tend to be associated with these cracks. So here's another example where there's a series of cracks, and then you see that the terrain right near the cracks is kind of softened and flattened as if something spewed out and coated the ground there. And this is a map of water ice where the dark blue is water ice. And so it seems like there's water ice involved with this deposit. And they're postulating a scenario, something like this, where there's a reservoir of molten water, lava on Pluto, and these cracks form and it comes spewing out. There's another paper by a grad student at MIT, Martin, and his professor Binzel, that pointed out that if you have an internal ocean and it starts to freeze, water expands as it freezes, right? So that stuff's got to go somewhere. So you gradually dial up the pressure inside that ocean, and eventually that can force some of the liquid out. The other thing is that as it's gradually freezing, the whole planet is actually expanding because it's made out of ingredients that are growing in size. It has to get bigger. And if you expand the planet, what you should see is pull apart or extensional tectonics like this. And you basically get blocks that drop down called graben, and the parts that stay up are horsts, and the faults between them are called normal faults. And those are exactly the same kind of tectonic patterns that you were seeing in these kinds of pictures. So it all holds together that the formation of the tectonics and eruption of something along them is driven by the slow freezing of Pluto's internal ocean. And that's probably happening right now because these tectonics are really very fresh looking. You see craters that are cut by the tectonic faults, but you don't really find craters often that are more recent. So that's telling you that the tectonics is more recent than the craters, and the craters just gradually accumulate over time. And so if you mostly see the tectonics cutting the craters, that tells you that the tectonics is relatively recent. So we think that this freezing of the ocean is actually probably still ongoing today and driving some of the internal activity of Pluto.
Well, we've got a couple more questions on that topic.
Yeah, go for it.
How many cryovolcanoes are thought to be there? How many cryovolcanoes are thought to be on Pluto?
Right. So there's the two really big ones, right? Mons and Picard Mons, that are not, we're probably fooling ourselves, but they're somewhat like the giant shield volcanoes like Mauna Kea and Mauna Loa on Earth, or Olympus Mons on Mars. But there's a lot of little things that look like, okay, there's a funny smooth area, or there's a funny exposure of water ice that in a place that we didn't expect to see it, or there's pits that don't look like craters because they're all clustered along a line, and impact craters don't do that much. They tend to be random, and so those are probably all related to some kind of eruption from the interior, but maybe different mechanisms for each of these different things. And to be honest, there's hundreds of them. They're really all over the place.
And another question: if there are faults there, does it mean there are also Pluto quakes?
Yeah, I think that would more or less follow. I suppose you could have a fault that happens very, very slowly and gently, but I think they tend to be kind of abrupt.
Yeah. And one more question.
Stress builds up and then it breaks, and then stress slowly builds up again and then it breaks again.
Hey, one more question for now from our friend Jeff Gagne. Is Pluto's ocean freezing because it's moving further from the sun in its elliptical orbit? Right.
Yeah, that's a good one. So Pluto probably formed closer to the sun when it first formed 4.5 billion years ago, at the birth of the solar system. It probably formed somewhere between 20 and 30 AU from the sun. AU is the Earth-Sun distance. And there was a bunch of early migration of planets that the most important of which was Neptune moving out and pushing a bunch of things further out. And that all happened pretty early on, and that put Pluto onto more or less its present orbit. And it's been there ever since. And Pluto's year is a long one, 2.5 centuries, but the and it's closer to the sun at perihelion and further from the sun at aphelion, but that thermal wave doesn't penetrate more than tens of meters into the ground. So the interior doesn't feel the perihelion aphelion difference at all. It's just slowly cooling over 4.5 billion years, just like the Earth's interior is. And one major source of heat is the decay of radioactive elements. So things like thorium and uranium and potassium-40 all break down very slowly over time, and they're in Pluto's deep interior, and their heat slowly leaks out. But there's less and less and less of them over time. And so that's why we're freezing now and why it didn't just freeze a long time ago. Okay, so next topic is what's in the haze. So there's this really spectacular haze layers, and I think I've got a photo later. I should have put one in first. But whatever's in the haze is important to understand because that's constantly painting the surface, and whatever chemistry is coming from the haze is going to be an important source of chemistry on the surface. And did I get my slides out of order here? I think I might have got my slides out of order, but or deleted a slide somewhere or other. Yeah, okay, so I had an intro slide to the haze that's gone. So the way the haze forms is up in the upper atmosphere of Pluto, there's methane, nitrogen, and carbon monoxide, and enough energetic radiation from the sun, ultraviolet light, to break the methane molecules. And the radicals that get broken recombine with each other and with other molecules to build progressively bigger molecules. And as those stick together and form larger and larger particles, they can't stay in the atmosphere forever, and they eventually settle to the surface. It might take them several years to settle to the surface, but they do. And there's a continuous supply of this stuff because the ultraviolet from the sun doesn't quit, and the methane in the atmosphere probably doesn't quit either. So a guy named Panagiotis Lavas, who's on my next slide, worked out models of haze formation on Titan, which also has very thick haze layers, and also Triton, which has somewhat thinner haze layers. And it turns out that there's a nice comparative planetology story there where on Titan, the haze is dominated by molecular growth. So you build up these really huge molecules that we call tholins. Skip back to, this is a picture of some of that stuff. It's dark and reddish, and it has just this really jumbly molecular structure with all kind of branches and chains and so on. It's kind of chemically very similar to like asphalt or tar, really thick, heavy stuff. Now on Pluto, you also get condensation starting to play an important role. And the main molecules that condense onto the haze particles are things like diacetylene, this one, and benzene, and various other hydrocarbons that are unsaturated in the sense that they have double bonds and triple bonds between the carbons, so there's fewer hydrogens. And that means that the ice that's in the haze is very carbon rich, and so it's delivering a lot of carbon to the surface. And what kind of chemistry that gets involved in is still being investigated, but it's probably pretty interesting. And then the last one is Triton, which is dominated by condensation, and so you get mostly lighter hydrocarbons and generally more hydrogenated hydrocarbons. So instead of like C4H2, you get C2H4, and so each of these different haze inputs to the surface is going to lead to different chemistry at the surfaces, and a lot of interesting chemistry that could happen in these different environments that are sort of analogous to each other, but different in their own ways. So this is good fun for a planetary scientist, having nature have run these different experiments for you in our solar system and be able to send a spacecraft to them and actually see what's going on there.
Well, how big are those haze particles when they reach the surface?
Yeah, they're very, very small compared to like the sand particles that we were talking about earlier. So the sand particles that we were talking about earlier were like a fraction of a millimeter, half a third of a millimeter. These are about a factor of maybe 300 or 400 smaller, so like a micron in size. definitely not the size you want to breathe into your lungs. I think this was supposed to be my first haze slide, so sorry about that. I got kind of garbled. But it's good to start with a picture so that you can see all these layers forming in the atmosphere and slowly accumulating on the surface. All right, well, that was out of order. Sorry. Okay, another way we're learning more about the materials that are on the surface of Pluto is to study them in the laboratory. And we have one of not very many laboratories in the world that can make these materials and hold them at Pluto temperature and pressure conditions and investigate them and see how they behave. And this is over at Northern Arizona University, just down the road from us. And among the things that we do there is we study the optical appearance of the various different ices that are on Pluto. And that's really useful for interpreting spectra that you took with a telescope or with a spacecraft. But we've increasingly gotten interested in thermodynamic properties of the ices, and you have all kinds of interesting effects when you get mixtures. And this is just one example of a mixture of methane and ethane. And under certain compositions, you form ice that's more dense than the liquid and sinks to the bottom. And under other composition conditions, you form ice that floats. And this is a more methane-rich ice that forms under this composition. And that really matters because if you imagine one of these glaciers on Pluto, if it melts at the base of the glacier and the liquid is less dense, it's going to want to come percolating up through the glacier and perhaps make plumes that erupt out of the surface of the glacier. On the other hand, if the liquid is more dense, like it is in water on water ice glaciers, it'll percolate down to the bottom where it's also probably the warmest, and it can lubricate the bed of the glacier so the glacier can move a lot faster. So if you want to understand how the geophysics is working, how these geological processes are shaping the morphology of the surface, you basically have to understand the properties of the materials. And we're really just learning how complicated these materials can be. They're weakly bound together, which is why they're volatile, by things like van der Waals bonds instead of the ionic or other chemical bonds that hold solids together that we're used to at room temperature. But they have all the complexity of like metal alloys, where you can combine strategic list of ingredients and have them undergo the right temperature history and end up with mechanical properties that are very, very different from the ingredients by themselves. And a good example of that would be like a steel, which is much, much stronger than iron and carbon, which are its two ingredients. Well, of course, there's other more complicated steels with nickel and chromium and other things too. A huge industry has evolved around making alloys and for specific purposes, turbine blades for jet aircraft or whatever. But none of that's really been done for these low temperature materials because, of course, there's not much commercial utility in them, but they're what makes the geology on Pluto work. So we want to understand those materials. Of course, telescopes are always important players. And before New Horizons, it was only a telescope game. And now we're back to barely resolved blobs of light. This is the best image of Pluto and Charon that you can get with the Hubble Space Telescope. And you can see there's basically barely resolved. You can separate Pluto and Charon from each other nicely, but you sure can't do geology on this. Now, the best telescopes in the world today can do about the same as Hubble, even ground-based telescopes, just because of adaptive optics to compensate for the effect of Earth's atmosphere. But you're not counting craters. You're not doing geology. What you can do is photometry, which is the measurement of the brightness of reflected sunlight. And that's sensitive to the surface texture and also the distribution of bright and dark regions. You can imagine if the globe rotates so that there's a dark region pointed towards you, it's going to look darker. And so you can monitor that over time. And this plot here on the right is showing the brightness versus the phase angle, which is just basically the angle between the sun, Pluto, and the guy in the telescope. And as that phase angle approaches zero, so that they're all three in a row, the brightness shoots up, and the full moon does this too. It's called the opposition surge, and that can tell you a fair bit of information about the texture of the porosity of the surface. Now, you can also measure the brightness of starlight as it passes through an atmosphere. I'll talk about that in a minute, but this is the variation as Pluto rotates. So the sub-observer longitude rotates through 360 degrees, and that has slowly changed over time because Pluto's aspect, as seen from Earth, has changed. We were looking in the northern hemisphere back in the 1950s when this light curve was taken, and the equinox was in the late 1980s. There's no light curve for that one, but now we're looking down on more the southern hemisphere, and the shape of the light curve has changed because you're seeing the various ices on the surface slowly migrate around over time. So these kinds of things, sort of for more seasonal timescales, are going to be key to understanding how Pluto's season unfolds. I mean, it's still only been less than half a Pluto year since it was discovered, so we haven't really seen the whole seasonal cycle yet, and won't for a while. This is an example of a stellar occultation where you're watching the light from a star. As the star dips into Pluto's atmosphere and is refracted, you see less and less light, and then it comes back out the other side, and you can invert that into the pressure, the atmospheric pressure, and usually that's quoted at some fixed constant altitude. In this case, it's 12, 15 kilometers. But you can see that from the late 1980s through the early 2000s, each of these points is another stellar occultation, and the atmospheric pressure has been going up and up and up. The error bars are a little confusing, this plot. The dotted ones are 3 sigma error bars, and the solid ones are 1 sigma error bars. So, if you're used to looking at 1 sigma error bars, the error bars are actually pretty modest in size here. So this last point that was published by Aramatsu et al. In last year, it really does seem to be showing a pretty dramatic drop-off. I guess I'll really believe it when somebody else comes in with another one and it's down here, but it does seem like stuff is changing on Pluto since the time of the flyby, which is right around here. And in fact, we might have actually just timed it perfectly so that we were there at the maximum atmospheric pressure. Spectrometry is just simply the same thing again, measuring how much light you're getting from the object, in this case, reflected sunlight, but at lots of different wavelengths. And the advantage of spectrometry is that it gives you composition because various different molecules vibrate at certain characteristic frequencies and tend to absorb the sunlight at those frequencies. So you can see methane bands are just all over the place in Pluto. I put a Triton plot on here too, so you can see the methane bands are weaker on Triton, but you can see some of the other species that are detected as well. Carbon monoxide has a couple of narrow features, nitrogen here. You can see it much better on Triton. Carbon dioxide has this narrow triplet, and then water ice has these relatively broad features here that in hindsight, now we know the reason this level of reflectance or about 1.5 microns is lower on Pluto than this one is because water ice is there, but you wouldn't claim that based on this spectrum alone. We kind of had to see it up close with the spacecraft to convince ourselves. If you take one of those absorption bands, like I think this is this CO band here, just this little guy, and just observe Pluto night after night after night, and then plot them versus the longitude that was under your, at the center of the disk that particular night, you see that it actually varies quite a bit as Pluto rotates. In fact, like a factor of maybe more than 2. And you remember this spot on the anti-Charon side is where Sputnik Planitia is, that big, bright glacier. And this tells you, even without visiting, now that we know what it is, that there's a lot of carbon monoxide ice there. And in fact, we did know this before we did the flyby, and that's part of why we targeted that hemisphere, was because we could see that something interesting was going on there. You can now collapse that even further and make a point for each year, where each year might be 6 or 10 nights at the telescope, and you can watch how things change over 2 decades in this case. And you can see that a lot of the volatile ices have declined over time. They're bouncing around a fair bit. There's considerable uncertainties when you do this, but Pluto is slowly changing over time. And that's the one thing that we couldn't do with New Horizons, is really see this long sweep of seasonal time. So we're kind of back in that game again now. Now, the future is really bright. There's new telescopes that are coming online with new capabilities. The European Extremely Large Telescope, EELT, has a 40-meter aperture, and the spatial resolution that you get from the telescope depends on the aperture and on the wavelength. So Hubble Space Telescope has an aperture of maybe 2.5 meters. So you can see that this is going to have a lot, and puts about a couple of pixels across Pluto. So you can see that this is going to go from a couple of pixels to a couple of tens of pixels across Pluto. And that's enough to really start to see the albedo patterns move around on the surface as it rotates. The American equivalent telescope called the 30-meter telescope has a 30-meter aperture planned for Hawaii. So the EELT is scheduled for first light in 2025. So that's not super far away that we've got to wait. The other future telescope that's going to make a big difference is JWST, the James Webb Space Telescope, which is above Earth's atmosphere, so it can see at wavelengths that don't make it through Earth's atmosphere. And that just gives us sensitivity to more different compounds in the atmosphere and on the surface. And JWST is, after a lot of delays, supposed to launch this October, and everybody's very eagerly looking forward to what it can do. And there are already Pluto observations scheduled for JWST, so we're going to get those results pretty soon, assuming that the schedule doesn't slip any further. Okay, and then last, there's a lot that New Horizons couldn't do because it was a flyby and it had a finite budget. NASA usually tries to do this paradigm where the first thing you do is a flyby for an initial reconnaissance, and then maybe you send an orbiter and then a lander and then a rover that can drive around and explore the surface, and then sample return, and finally send a human crew. We haven't got that far with anywhere except for the moon. And I don't think that's going to happen anytime soon with Pluto because the travel times are kind of long. But you can imagine that an orbiter or a lander could really do all kinds of amazing science. For starters, just seeing the sides of Pluto and Charon that we didn't get close-up looks at, and watching things that change on a timescale of a day or timescales of a month. There's a lot of active processes going on Pluto, and just being able to stay in orbit and watch them unfold would really shed a lot of light on what's going on. We've learned a whole lot about Mars from having a fleet of orbiters staring at the surface as the seasons unfold. And then, of course, you just get better quality imagery just because you're closer and you can spend more time collecting it and radioing at home, and collecting more and radioing more of it home. So I think that is my last slide. Yeah. And so I'd be happy to take more questions. I try to leave a fair bit of time.
Okay. Yeah, we've got several questions lined up, kind of a diversity of questions. So let's just start going through. Another question from the Pluto Diaries. How many craters have been counted so far on Pluto?
Okay. So I'm not a crater counter myself. But it's thousands and thousands of craters, and I don't have the patience for that or the eyesight. But a couple of people like Stuart Robbins and Kelsey Singer at Southwest Research Institute have meticulously counted craters, and there's a lot of things on Pluto that might be a crater and might not be a crater. Like, is that a crater? Okay, this is the crest of that putative cryovolcano. But so what they do is they work independently of each other, and then they compare their notes. And if everybody agreed that something was a crater, then you'd give it a high confidence. And if only one person did, then you give it a lower confidence. But it's really important to do that because the statistics of the craters can tell you a whole lot about how old the surface is, and also about the environment that Pluto lives in the Kuiper Belt. How much small debris is flying around out there that can make craters.
And how does the amount of cratering on Pluto compare to cratering on other planets?
Yeah, so we were kind of surprised at how it's not completely peppered with craters like the way the Earth's moon is, where basically everywhere you look on the moon, you see craters on top of craters on top of craters. And Pluto has many areas that have no craters whatsoever, like Sputnik Planitia. So that tells you that that's refreshing its surface on a very short time scale, maybe shorter even than 1 million years. But there are also some heavily cratered regions. Charon is maybe a better test of the cratering population, just because it's probably not very geologically active anymore. So there's no mechanism to really erase the craters. But even there was a sort of a paucity of small craters, which points to somewhat of a paucity of small Kuiper Belt objects. So it's not like the inner solar system, where things are moving a lot faster just because they're deeper down in the sun's gravity well, and there's a lot of debris from the asteroid belt that gets into the inner solar system and pokes holes and things.
Okay, here's another question from Jeff about methane. Why does the outer solar system seem to have a lot more methane than the inner solar system?
Yeah, that's an interesting question. Carbon, nitrogen, and oxygen are the next 3 most abundant elements after hydrogen and helium. And if you take oxygen and put it with hydrogen, you get water. If you take methane and put it with hydrogen, if you take carbon and put it with hydrogen, you get methane. If you take nitrogen and put it with carbon, you get ammonia. So those 3 ought to be kind of ubiquitous. But water can take the heat a little bit better than methane and ammonia can. So I guess that's why they're tending to be scarcer, closer to the sun. But there's plenty of methane in, say, Jupiter's atmosphere and the atmospheres of Saturn, Uranus, and Neptune. So it's not like it's only in Pluto. It's just we don't have much here at Earth.
Okay. Here's a question from Ken Sands. How did you deduce the composition of the core?
That's takes a bit of a leap of faith. So the most common building blocks of planets in the solar system are water ice, or water, and rocks. And so when you measure the density of something like Pluto, and you get a density about 2 grams per cubic centimeter, water has a density of approximately 1 gram per cubic centimeter, rocks are sort of more like 3.5 grams per cubic centimeter. And so this is halfway in between. The simple back of the envelope math is to say, okay, it's 60% rock, 40% water by mass. However, there are other possible ingredients that we could be ignoring, one of which is metal, which is even denser. Another of which could be very important in the outer solar system, is carbonaceous material, sort of this crude oil kind of tar, asphalt, whatever, carbonaceous mess. And if there's lots of that in the interior of Pluto, then there must be less rock, and we don't really know what that ratio is. So it's kind of conjecture. This is the sort of thing an orbiter could do, where it could actually probe the interior mass distribution, but we couldn't do that with a flyby.
Okay, here's a question from Destiny Madahe. Are there any anomalies in Pluto that science can't make sense of? You
mean like the alien city in the southern polar region? Oh, well, I'm supposed to say that. No, there's a lot that we don't understand. This is how scientists work. We go there with a set of questions that we put in the proposal, and we might have answered those questions or learned that they were dumb questions. But all of the new data just triggers far, far more questions. And we certainly haven't answered them all yet. So that's why all of this research activity is still going on. And just looking at this picture, you can see there's various bright regions on the surface of Sputnik here. This is the edge of Sputnik, and some of them match up to pits in the surface of Sputnik, and there's also dark ones that match up to pits. And so, why are some of them dark and some of them are bright? Is it that something's actually like vapor is escaping from some of those pits, and that's forward scattering sunlight towards us? There's lots of puzzles. By now, a lot of the weird puzzling terrains that have been seen have papers published suggesting hypotheses for how they formed, but it's very hard to actually prove that those hypotheses are right, because who knows whether somebody's going to come along in 5 more years and come up with a better idea.
Okay, Stephen Silver asks, will Pluto's atmosphere remain gaseous as the planet moves towards aphelion?
Yeah, that's there's been a lot of published on that and a lot of opinions on that. Certainly when we were proposing the spacecraft 25 years ago or 20 years ago, one of the arguments we made was, well, it would be a shame to wait till the atmosphere collapses because the atmosphere is involved with a lot of these surface processes. It would be nice to see that in action. Subsequent to that, people have done some models that suggest that it never collapses. It gets thinner, but it doesn't collapse. And by collapse, I mean it gets so thin that it can't blow winds gracefully around the surface. It's more like an exosphere or something. So we don't really know, but the stellar occultations are going to allow us to see what happens over time. And if that paper from 2020 is right, it looks like it is dropping off abruptly. So it will be well worth watching it over the next 5 and 10 years even, let alone the next century and a half of the rest of the first Pluto year since its discovery.
Okay, here's a question from Kathy. Does Charon's orbiting of Pluto produce any heat in Pluto?
Yeah, so it's a circular orbit pretty much. So it doesn't raise tides in Pluto. They're tidally locked to each other, although the process of getting them tidally locked would have dissipated energy and put small amounts of heat into the interior of Pluto. I don't think probably all that important compared to the radioactive decay, but maybe if there's less rocks than we thought and more carbonaceous material that's not radioactive, maybe it is more important. There are also the 4 small moons that perturb the system ever so slightly. They're not very massive, so they're not really enough to have a big effect. But so a lot of the thinking about what drives activity in cold, icy bodies came from the Voyager spacecraft flying through the Saturn, Uranus, Neptune system and seeing satellites that looked like they had some geological activity or still were geologically active, like Triton. And because they're in the presence of a giant planet and sometimes in eccentric orbits, there's a good source of tidal heat there. And so the expectation was that source of tidal heating can't work on Pluto, and so it would be geologically dead. It obviously isn't, but that's probably because it can make do with smaller amounts of heat from the radioactive decay.
Okay, here's a question from our friend Jim Davies. Hello, Jim. Have we noticed a retrograde motion in Pluto's orbit?
So are you referring to the perception that it's going backwards as seen from Earth because of the Earth's motion around the sun? I'm not totally sure, because Pluto goes around the sun the same way that all the other planets go around the sun. It's prograde, not retrograde.
Yeah, so I guess to answer that in the best Yeah, the assumption, the appearance of it.
Yeah, so that happens, but that's really the Earth's motion that's doing that. It's because we're moving so much faster around the sun every year.
Yeah. Okay. Another one from the Pluto Diaries. What would it be like to walk across Pluto's heart, particularly Sputnik Planitia? What would the view be and the feel of walking in the soft ice?
Yeah, I would really like to know. And how soft is the ice? So we can make nitrogen ice in the lab and poke it, and it's squishable. But I don't really know whether alloys of nitrogen ice are as squishable. So the smallest pixels that we were able to put on Pluto from New Horizons were maybe 70, 80 meters across. So it's like the size of a football field. And if you're walking across a landscape, you're looking at things that are, inches across, centimeters across, feet across. We couldn't see any of that. And so it's just our imagination to see what kinds of processes might be acting at that smaller scale. In fact, we were busily working on it this week and last week, organizing a workshop for this coming summer on how the surface of Pluto's volatile ices should evolve on those kinds of spatial scales, and what kind of analogs we can draw from, say, the polar regions on Mars, where there are similarly frozen gases from the atmosphere that then sublimate away in the spring. And if you look at some of the Martian polar images, you see just some absolutely wacky landforms. You see these plumes that are driven by solar energy, where the sunlight goes down into the ice and warms the subsurface, and pressure builds up down there, and eventually it cracks and you get these vents spewing out and blowing dust up into the air. Google Swiss cheese terrain sometime and you'll see some really amazing Martian polar landforms, and that sort of thing could also happen, and that might be on the sort of the spatial scale of somebody hiking. So there's a lot to think about. And of course, nitrogen ice is amazingly transparent, so you might be able to see quite a ways into the ground, especially in regions where the ice has sat for a long time, and so it's maybe sintered together into a more clear slab of ice than more of a granular texture.
How about a place like Tartarus Dorsa? The spikes, are they miles apart or closer?
Yeah, so they're, I'm trying to remember, I think they're about 1 kilometer across or spacing between them, and they're hundreds of meters tall. So they would be some treacherous terrain to navigate, a lot of up and down and a lot of up and down. But yeah, some really spectacular scenery out there.
Well, here's a question from our old Pluto friend, Laurel Kornfeld. Could there be microbial life in Pluto's subsurface ocean?
Right. So there have certainly been people that have argued that these interior oceans are potentially habitable environments. You've got water, which is something that we think is needed for life. You've got a ton of organic material. You've got a source of internal heat energy, and you could potentially have hydrothermal circulation of the water through the mantle that's heated by the radioactive decay. And so you could get these, the moral equivalent of the black smokers down at the bottom of the ocean on Earth, which are very lively biological sites, because there's a lot of chemical energy in the heated water that's coming out of those hydrothermal systems. So I guess it's kind of a two-part problem: is if could you get life there in the first place, and then could you sustain it? I think it could be sustained I think that would be not too difficult, but would life arise in such a place is less obvious, because we don't really understand how life arose on Earth.
Okay, here's another question from Ken Sands about the timing of sending an orbiter. Would such a thing happen in your career or well after your retirement?
I know that NASA is doing studies right now of potential orbiter missions, and there's many people who would like to see it happen, including some of the younger people on the New Horizons team who could plausibly live to see it happen. It wouldn't be cheap, and it's critically dependent on some technological developments. Anything you can do to miniaturize the instruments, miniaturize the communication system. The smaller the spacecraft can be, the easier it is to fling it out to Pluto. The easier it is to slow it down once you get there. So I wouldn't rule it out. It depends a lot on what NASA and the scientific community think are priorities. And every 10 years, the community goes off and does a huge study of what should be its scientific priorities for the next decade. And one of those studies is going on right now. This is the time for it to set the stage for the next decade's worth of exploration. And so we'll see what comes out of that study. I know that there's lots of people that would be interested in doing it. But of course, there's many other interesting targets for exploration too.
I'll point out that we have a special reason to look forward to an orbiter here at the observatory. About 12 feet from where I'm sitting, we have a time capsule that has dozens of pieces of Pluto memorabilia and scientific papers and other things, not to be opened until the first orbiter reaches Pluto. So we'll look forward to opening that one of these days. One last question. I think this is a good one to end on from Lana. What single feature on Pluto excites you the most?
Boy, it's quite a smorgasbord. I guess something I'm interested in looking into a little bit more is there's some pits that nobody's really published on just east of Sputnik, where they're kind of conical in shape, and their spatial distribution doesn't look like impact craters. And I'm pretty sure something erupted out of them. And some of them show water ice signatures, which tends to get buried pretty quickly on Pluto. So that suggests that they were maybe active now or very recently. So I'd like to work a little bit more on those. I'm getting the impression from looking at the surface that there's a lot of plumbing going on below the surface, and some, the equivalent of hydrothermal fluids or aquifers moving around below the surface and erupting out in different places than where they went down. And that's the sort of thing an orbiter could do, is peer down into the ground with radar and see what some of that plumbing looks like. That would be really interesting to me.
Okay, well, thanks so much for joining us tonight. As so often happens in science, the more we learn, the more questions we have. And so there's a lot of really great future science to be done in the outer solar system and Pluto. So thanks, Will, for joining us tonight. Thanks to our technical team, Danielle and Heather and Richard, for making everything work. And thanks everybody for joining us. Have a great night.